Okay. One of the most important register but more mundane thing to study, especially at the end of the day, is this EFLAGS extended flag register. Flags are very important. As I told you in one of the examples there, where I made a jump less than or equal to, do you remember in one of the session, and that is because of the flags. I do an operation and the result of the operation, not the data part, the characteristic of the result of the operation is captured in the flag, right. I do compare of two numbers. If the number on the left hand side is less than the number of the right hand side, the less than flag is set. If it is equal, the 0 flag is set. If it is greater flag is set. So lot of so the whole program, many of the program we write is very complex. How do you characterize complexity in programming? Lot of logic statements that we do, lot of case statements that you do, not a lot of nested ifs that you do. This is how your logic is getting complex, right. All straight line programs, this instruction, next, all sort of numerical computation, those are not complex to the mind, right. It is complex to the system because it needs to do a lot more arithmetic operations. The logic operations actually determine the complexity of a program, and all these logic operations basically get translated to conditional branch instructions. If j is greater than k, max is equal to j, else max is equal to k, actually translated into a conditional branch instruction as we saw in one of the previous sessions. And these conditions are basically evaluated by this, by seeing the EFLAGS register. So at the end of every arithmetic operation, the flags get updated and the subsequent conditional jump instructions look at this flag. So that is one of the precise reason why we want to spend some time to basically talk about this EFLAGS register, right. Now in this EFLAGS register, there are 32 bits read from left to right, right to left, and the bits 1, it is numbered 0 to 31, the bits 1, 3, 5, 15, 22 to 31 are reserved. We do not know what it is intended for. As of now, as programmers, we do not find anything there. The 18th bit is called alignment check, the 19th bit is called VIF, 20th is VIP, 21 is ID, and then all the other things are here. So let us basically look at some of this bit. So there is a bit for carry, this is called a carry flag. This is set by arithmetic instructions that generate a carry or borrow, and this is basically necessary sometimes to detect overflow, underflow, etc. It can be set, inverted and cleared by what we call as set carry instruction, clear carry, and complement carry, okay. And there is also something called a parity flag, which is set by most instruction if the least significant 8 bits of the destination operand contain an even number of ones, right. This is a parity flag, and this is very important for some error checking and other type of activities. There is an auxiliary flag if a carry or borrow from the most significant nibble of the least significant byte, okay, right. So the least significant byte is 2 nibbles, the most significant nibble is the later part of the least significant byte, and if there is a carry it will be set. And where do you use this? We use it in BCD arithmetic. And why is BCD arithmetic very important? Because all your things are binary coded decimals, right. Many softwares work on binary coded decimals, right. You know what is binary coded decimals? So you do from 0. So all your thing is not hexadecimal, right. Your Excel does not work in hexadecimal, right. You go mad if you start using reading hexadecimal numbers or binary numbers. So you are still accustomed to decimal arithmetic. And so how do you perform decimal arithmetic? Using binary coded decimals, and this is BCD is very important. The 0 flag is set by most instructions if the result of the operation is 0. There is a sign flag which gives you whether the signed operands, this tells whether the result is positive or negative, and that is how we do compare, okay. So compare, how do you compare A and B? You subtract A and B. If the result is negative, A is less than B, result is 0, A is equal to B, result is greater than 0, suppose result is positive, it is greater, right. So the sign flag is also very important. And then these are all flags which are basically set by operations, and you will go and find like some characteristic attribute of the result. Now there are flags which are used to control your execution. For example, trace flag. On being set, it allows single step through programs, right? You want to do single step through, right? So what it does, allows you to go one step, then it will take you to interrupt service routing. There you go and do something, you check what are the things, again it will resume back and do. So this allows you, it generates an interrupt at the end of every instruction so that you could go and find out what that instruction is doing. To essentially, these are all used for debugging. Okay. Okay. So there is another interrupt flag which is basically when set, the processor recognizes the external hardware interrupts on INTR pins. If you reset it, if you clear it, it has no effect at all. So even if you interrupt, nothing will happen, correct. So the simple way by which somebody can hack into your system is to go and reset this, clear this interrupt flag. Then you go and do any interrupt except all non-maskable, every external non-maskable interrupts, correct, it will never recognize. The system will do some execution, then you go and set it back, then it will recognize. So these are very, very important flag. From a security perspective also, this is very important. So this flag can be set and cleared using STI and CLI instruction, okay, right. So slowly let us try and understand every flag from a security perspective also, right. What will happen if I disable all interrupts? You lock the system from the user, correct, it is a denial of service, right. Then, so that is one of the reason why we will see later that your STI and CLI, right, the set interrupt and the clear interrupt are called privileged instructions. They can be executed only when the processor is executing at the highest privilege, right. We will talk about it as we go, right. And when it is in the highest privilege, so if you get a privilege gain, then the first thing you will go is to go and screw up this interrupt, okay, then you are isolated, then you do whatever you want, okay. So please understand the thing. So this is what this course is adding. So all these things are available in Intel developer manual. What is it that you are doing? No, you will ask me this question. This extra masala is what I am adding here from a security perspective, okay. So there is something called a direction flag specifically for string instructions. So one flag is dedicated for string instruction. So I said, right, there is a segment register, there is an offset, there is another segment register, another offset and a counter. So that from that segment register base, that offset to this segment register, this offset, copy this many bytes. Should I copy it in the forward direction, should I copy it in the backward direction? That is a question, right. This direction flag will tell you, right. This direction flag will tell you it will increment or it will decrement, right. It will tell you whether in this direction should I go or in the opposite direction I go, okay. So that is also very interesting. And there is a overflow flag which is very important. Most arithmetic, this is something again, arithmetic instructions will set this flag to indicate that the result was at least one bit too large to fit in the destination. IOPL, this is also a very important flag. So this is set by the operating system, right. When I want to do an IO, right, so the processor will execute in 4 privilege levels 0, 1, 2, 3. Why 4? We will talk about it in subsequent session. 4 privilege levels means how many bits I need to represent these 4 privilege levels? 2 bits I need. So the bits I set here, if I set it as 3, that means any process can use it 0, 1, 2, 3. But if I set it as 2, then the process at privilege level 3 cannot do any IO at all, okay. So for protected mode operation indicates the privilege level 0 to 3 at which your code must be running in order to execute any IO related instructions, okay. So meaning that and below. So 2 means 2, 1, 0, 3 means 3, 2, 1, 0, 1 means 1 and 0, 0 means 0. Okay. So, this is very, very important for you to understand here. And then there is something called a nested task flag. When set, it indicates that one system task has invoked another through a call instruction as opposed to a jump. So, what is nested task? I call you, after you finish it has to come to me, not to something else. What is jump? I call you, then you execute. There is no necessity for you to come back. So, that is the difference between jump and call. And this nested, for multitasking, this can be manipulated. This is very important for nested task, this flag. Then there is something called resume flag. It is related to debug registers DR6 and DR7. By setting this, you can selectively mask some exceptions while you are debugging code. This is basically used for debugging. But then, can we exploit this to gain some information about the code? So, I have some code. For example, I have a licensed code and it is accessing some license file, correct, to validate so that it can execute. Right? Can I use this debug registers to go and get some details of how to break this license? It is a very interesting exercise, right. There are some positive answers to that question. Then there is virtual 8086 mode. I think nobody uses it, but still it exists for this thing. Now comes two more flags that are dictating about one flag that is dictating about performance, which is called an alignment check, right. So, when you look at a complex instruction set computer, it has 8-bit operands, 16-bit operands, 32-bit operands. From the memory, when I am getting an instruction, I read it as 4 bytes. When I get data, I read it as 4 bytes, 4-byte chunk. So, if I want to read byte 1, I read 0, 1, 2, 3. I can't just read only 1. If I want to read byte 2, what do I read? 0, 1, 2, 3 only. In that 4-byte segment to which it belongs, I read all those 4 bytes. If I want to read byte 3, then I read 0, 1, 2, 3. So, suppose my byte is stored, I now want to read a double word which is 4 bytes, and that byte is stored in 2, 3, 4 and 5 memory locations. So, to read this, what will I read? First I have to read 0, 1, 2, 3, then 4, 5, 6, 7. So, to read one operand for me, it takes 2 memory reads. You understand this, right? Please understand this. So, always the data that comes from the memory to the cache is 4-byte blocks, right. So, some instructions can become really slow. Do you understand this? Because instead of reading 1 byte, I am reading 2 bytes. So, essentially it becomes slow. So, if I had stored that byte as 0, 1, 2, 3 instead of 2, 3, 4, 5, the worst case is 1, 2, 3, 4. So, I read that. If I had done it like that, then it would have been very easy. So, imagine I have 1 million variables and every variable is not aligned, then what will happen? Your memory performance actually screws up, right, very badly, right. So, this is, and they are on different locations, quite spread out. So, this becomes an extremely complex. So, what do we do is there is a flag called alignment check. That alignment check essentially tells if it can talk about bit aligned, it can talk about word aligned, but here it talks about word aligned. If it is not in this 32-bit boundary, that is, it should be, if a variable starts, it should be 0, 1, 2, 3 or 4, 5, 6, 7, or it cannot be between half of this and half of this. If it is going to be in the half, it will immediately give us an exception. So, when you compile the code, make the alignment check flag as 1 and run this code, and wherever you are finding this misaligned access, it will flag an exception. Then you go and do some changes so that you align it. Finally, you get an aligned code, and the moment you have an aligned code, your performance will be very fast. What do you mean by performance tuning of architectural level performance tuning of your code? This is what you mean by that. Right. So, you see to that the alignment is proper, so that when the code executes, no memory fetch actually becomes 2 fetch, it becomes a single fetch. So, this is a way by which you can do performance tuning on your code, right. That is the alignment check flag, right. and you go and clear it after everything is done, you can clear it, then but your code will really become fast. So what do you lose by this? Right? If I have some 2-byte variable, if I have 4 2-byte variables, in a non-aligned setup I can put it in 8 bytes. In an aligned word setup I should put it in 16 bytes. Your memory actually doubles. So I go back to my communist signs, okay. You lose something, you gain in performance, you lose in memory. You gain in memory, you lose in performance, okay, right. Are you able to follow this? Okay. The bit 19 is called a virtual interrupt flag, which is a virtual image of the interrupt flag. This is used in conjunction with the VIP flag, okay. So there is something called a VME flag in the control register 4. So there are so many things, but I should tell you that all these things are much related to what you call as the system management mode, right. This gets, so we will talk about SMM possibly sometime down the line, probably a part of this course or part of the operating system course where it will become. So but do remember there is a VIF flag and a VIP flag which basically are used for certain operating system related functionalities, okay. And the last one is the ID flag, which is the identification flag. The ability of a program to set or clear this flag indicates support for the CPU ID instruction. So I can get, so every CPU that is produced has a unique ID and you can get that ID, okay. Then there are certain protected mode registers. These things will become clear tomorrow, but do understand that there is a local descriptor table register, a global descriptor table register, an interrupt descriptor table register and a task register of 16, 48, 48, 16 bits respectively. Just note it down, and tomorrow when we deal with segmentation in greater detail, we will understand where these are used. Okay. And so we have talked already about control registers and debug registers, and then there are test registers which are used to perform confidence checking on the paging memory management units translation look aside buffer. So what is translation look aside buffer? What do you mean to do confidence checking on that? Those things we will see as we go through the virtual memory concepts. But there are some registers called test registers. So what I have done today is to tell you the infrastructure that is available for computing, the local storage infrastructure that is available for computing, namely the registers and some of the registers which are used for controlling the program, okay, namely the flag registers. So with this we come to the end of session 9.